Welcome to the Explainer. If you're a chemistry student, you know that figuring out the exact concentration of a solution is a huge deal. Well, today we're breaking down one of the most powerful techniques to do just that, titration. We're going to walk through it step by step so you can totally master the concept.
So let's kick things off with a classic chemistry problem. Imagine you've got a solution. You know what's in it, but you have no clue how much of it there is. How in the world do you measure something you can't even see? Well, that's the exact puzzle that titration was designed to solve.
And here's our roadmap to get you there. First up, we'll get the basic definitions down in what is titration. Then we'll zoom in on the most important moment of the whole reaction, the equivalence point, and the math that makes it all work in the equivalence relation. After that, we'll look at the experimental setup and tie it all together with a real-world example, titrating iron 2.
All right, let's dive right in. Look, to really get a handle on titration, you've got to speak the language. So let's get our core vocabulary straight, because these terms are the absolute building blocks for everything that follows.
First up, we have the word dosage. This is just a really broad general term for pretty much any technique you'd use to figure out the concentration of a substance. Think of it as the big umbrella category for what we're doing. Now, titration is a specific kind of dosage. It's our main tool for this job. And the key thing to remember is that titration uses a very carefully controlled chemical reaction to hunt down that unknown concentration. In any titration, you've got two main players. The first one is the titrated species, which you'll also hear called the analyte. This is our mystery chemical, the one with the unknown concentration that we're trying to figure out. You'll usually find this in the flask waiting for the reaction to start. And our second player is the titrant. Now this is our secret weapon, our measuring tool. It's a solution where we know the concentration precisely. We add this stuff carefully from the burette, and it's the key that's going to unlock the whole measurement for us.
Okay, now let's see what happens when these two solutions actually meet. We're heading towards the most critical moment in this entire process, the equivalence point. This is where the magic happens, and it's where we get our final measurement.
You can really think of the reaction happening in 3 acts. Before the equivalence point, any titrant you add gets immediately gobbled up by the analyte in the flask. Then, after the equivalence point, all the analyte is gone, so the titrant starts to build up. And right there in the middle, that's the sweet spot, that perfect moment of balance we're looking for. So let's be super precise here. The equivalence point is that exact moment when the amount of titrant you've added has perfectly, completely reacted with the analyte in the flask. It's a perfect chemical balance. Nothing is left over, no excess titrant, no excess analyte.
Now, this is absolutely crucial. How do we actually see this equivalence point? I mean, it happens on a molecular level. Well, here are the two most common ways. In case 1, if your analyte is colored, you'll know you've hit the equivalence point the second the solution turns colorless. And in case 2, if your titrant is colored, you're there the moment the solution gets a color that just won't fade.
Spotting that color change is the first big step, but how do we turn that visual cue into a number? That's what this next part is all about. We're going to cover the simple, kind of elegant math that lets us calculate our unknown concentration. The entire calculation, everything we're about to do, hangs on this one single idea. At the equivalence point, the reactants are mixed in perfect stoichiometric proportions. All that means is the ratio of what we've mixed together perfectly matches the ratio from the balanced chemical equation.
And that one simple principle gives us this incredibly powerful formula. Here, N is just the number of moles, and A is the stoichiometric coefficient. You know, that big number in front of the chemical in a balanced equation. So the moles of our analyte divided by its coefficient is equal to the moles of our titrant divided by its coefficient. This is our foundation.
Okay, now we can start plugging things in. You probably remember that moles equals concentration times volume. So for our analyte, species 1, its moles, N1, equals its unknown concentration, C1, times the initial volume we put in the flask, V1. That C1 is the prize. It's what we're trying to solve for.
And we do the exact same thing for the titrant, species 2. The moles we added, N2, equals its known concentration, C2, times the volume we added from the burette to get to that equivalence point. We call this special volume VE. And it's the key value we actually measured during the experiment. And now, for the final step, the big reveal. We take those two expressions for N1 and N2 and plug them back into our main equivalence equation. With just a little bit of algebra, we rearrange everything to solve for C1, our unknown concentration. And just like that, We've done it! By knowing 3 things and measuring just one volume, VE, we've found our answer.
Okay, the theory is solid. I think you'll agree. But let's get out of our heads and onto the lab bench. How do we actually do a titration? This is the classic setup you'll see in pretty much any chemistry lab. Here's the essential gear. You need a burette, that long glass tube, to add the titrant super precisely. You'll need a pipette to measure out your analyte perfectly into the flask. An Erlenmeyer flask is where the reaction happens, and a magnetic stir is key to make sure everything mixes instantly. And the procedure itself is very methodical. As you can see, first you fill the burette with your known titrant solution. Second, you use a pipette to transfer a precise amount of your unknown analyte into the flask. Third, you get that stir going, and finally, you add the titrant drop by drop, watching like a hawk for that permanent color change that tells you you've hit the equivalence point. So let's put all this theory into action. Let's walk through a classic, super common lab experiment. Titrating iron 2 ions with a solution of potassium permanganate. So here are the players for this reaction. Our titrant, the stuff in the burette, is the permanganate ion, which has this really intense violet color. And our analyte, the mystery solution in the flask, is the iron 2 ion, which is totally colorless. So, based on what we just learned, what do you think we're looking for? What's the visual signal going to be?
You got it. This is a perfect example of case 2 from earlier. As long as there's any iron 2 left in that flask, the violet permangate we add is instantly used up and the solution stays colorless. But the very first drop of permangate that falls in there and can't find any iron 2 to react with, well, it gets to keep its color. And that one drop turns the whole solution a faint but permanent pink. That's our signal. That's the equivalence.
And there you have it. That's the full framework. Titration gives you this clear, visual method, backed by some really straightforward math, to find an unknown concentration. And the real power here is that this is such a flexible technique. So here's a final thought to take with you. If you needed to figure out the concentration of, say, sulfur dioxide, or SO2, how would you adapt this protocol? What kind of titrant might you use? And what visual cue would you be looking for? Once you can start answering those kinds of questions, you've really mastered the principle.